Mangrove ecosystems are among the most valuable coastal habitats on Earth, providing critical ecological, social, and economic services. They protect shorelines from cyclones, floods, sea level rise, coastal erosion, and intense wave action, while supporting fisheries and sustaining local livelihoods. Mangrove forests rank among the planet's most productive ecosystems, delivering essential biodiversity support and forming natural coastal defenses. Their canopy structure protects understory species from harmful solar ultraviolet radiation, while their exceptional capacity to sequester atmospheric carbon enables them to capture carbon at rates 3 to 4 times higher than terrestrial forests, positioning mangroves as powerful nature-based solutions for climate mitigation and greenhouse gas reduction. Despite their global importance, mangrove ecosystems have declined significantly in recent decades, particularly in developing countries. Major drivers of loss include urbanization, land reclamation, industrial expansion, pollution, resource overexploitation, and aquaculture development. Over the past 20 years, global mangrove coverage has decreased by approximately 35%, posing serious threats to long-term ecosystem stability. Climate change further intensifies these pressures through rising sea levels, altered species distributions, and increased natural disturbances, collectively reducing biodiversity and weakening ecosystem resilience. Effective conservation of mangroves requires integrated coastal management supported by systematic monitoring, strong governance, and sustainable resource utilization. Advances in remote sensing and GIS technologies have greatly improved the ability to map mangrove distribution, detect temporal changes, and guide evidence-based conservation decisions. Rehabilitation approaches have demonstrated measurable benefits such as enhanced carbon storage, improved fisheries productivity, and strengthened coastal protection. However, many restoration efforts fail due to insufficient planning, weak governance, and limited stakeholder engagement, underscoring the importance of science-based and participatory approaches. In Egypt, mangrove ecosystems are represented by 2 species, Avicennia marina and Rhizophora mucronata, distributed across approximately 28 sites, covering nearly 650 hectares along the Red Sea coast. Avicennia marina dominates northern and central zones, whereas Rhizophora mucronata occurs only in the far southern region. Due to its wide distribution, A. marina serves as the most suitable indicator species for monitoring the Egyptian Red Sea mangrove ecosystem, which remain ecologically significant, supporting marine biodiversity, enhancing coastal stability, and sustaining local livelihoods. Nevertheless, they face increasing threats from coastal development, tourism expansion, pollution, and climate-related hazards, particularly in central and southern regions. Since 2003, multiple national and international initiatives have been implemented across Sinai and the Red Sea, achieving partial success in selected areas. Within Wadi el-Gemal National Park, located approximately 50 kilometers south of Marsa Alam, only Avicennia marina is present within the park, forming 11 recorded stands, including 2 located on offshore islands. In response to increasing environmental pressures, the Support Nature Conservation Sector in Egypt project, funded through the Italian-Egyptian Debt for Swap program in coordination with UNDP, implemented an integrated rehabilitation program. The project aimed to restore grey mangrove populations, including the production and planting of 1,000 seedlings, strengthening technical capacity, and establishing standardized monitoring protocols aligned with internationally recognized conservation frameworks to ensure long-term sustainability. Prior to initiating ecological surveys and rehabilitation activities, an intensive planning phase was conducted, focusing on capacity building, stakeholder engagement, and knowledge exchange. During this phase, a series of structured meetings, participatory consultations, and technical interviews were carried out with park staff, researchers, and representatives of local communities across multiple generations. Training workshops were delivered early in the project timeline to strengthen the technical readiness of field teams and community members before the commencement of site assessments. These workshops focused on GIS mapping and spatial modeling, species distribution modeling, seed collection techniques, nursery management practices, and monitoring protocols. Conducting these activities during the planning phase ensured that all stakeholders possessed the necessary technical knowledge and shared understanding before field implementation began. Community engagement was a central component of this preparatory stage. Structured interviews and participatory meetings enabled the documentation of traditional ecological knowledge, identification of degraded mangrove areas, and validation of historical ecosystem changes. These discussions also contributed to defining locally acceptable rehabilitation strategies and strengthened trust between project teams and local community. Following completion of the planning and capacity building phase, the first major technical phase focused on ecological site assessment and spatial mapping. Data collection and analysis were conducted through an integrated approach that included desk-based reviews, satellite imagery analysis, stakeholder consultations, and extensive field verification. These efforts aim to determine geographic ranges, population characteristics, ecological attributes, habitat conditions, and threat levels based on the IUCN Red List classification scheme. Using satellite imagery obtained from Sentinel and Landsat platforms combined with GIS-based spatial analysis, we mapped mangrove distribution patterns, density hotspots, and environmentally sensitive areas. Field surveys were conducted to validate remote sensing outputs and document key ecological parameters, including canopy cover, habitat condition, regeneration status, and threat intensity. Subsequent analytical stages involved hotspot mapping, site prioritization, and sensitivity analysis. This process generated threat overlays and produced a comprehensive technical report containing conservation recommendations developed in accordance with mapping standards and data quality requirements for IUCN Red List spatial data. This integrated methodology produced a scientifically robust baseline describing the ecological status of mangrove habitats within Wadi El-Gemal National Park. The assessment confirmed that mangrove ecosystems within the park are distributed across 11 key locations covering approximately 1.65 square kilometers. Spatial analysis revealed substantial variation in stand structure, ranging from dense and mature forests in the Hamata sector to fragmented and low-density patches in other locations. Tree heights generally ranged between 1.5 and 4.5 meters. Mangrove distribution patterns were found to be strongly influenced by geomorphological characteristics, tidal exchange processes, and sediment availability. Despite the presence of locally stable stands, the ecosystem overall remains fragile and fragmented. Major threats identified include overgrazing, wood harvesting, coastal development, pollution, and natural stresses, all of which collectively limit regeneration capacity and threaten long-term ecosystem stability. Based on the results of the site assessment, the rehabilitation process commenced with the development of a conservation action plan aligned with IUCN SSC guidelines. This intervention was designed as a targeted, small-scale rehabilitation strategy intended to enhance existing healthy mangrove stands, rather than implement extensive large-scale restoration. Site selection followed a strict set of criteria, including environmental protection from waves and flooding, vegetation continuity and density, climate resilience potential, presence of reversible human impacts, documented success of previous rehabilitation efforts, and geomorphological suitability, such as tidal creeks containing sand-clay organic substrates. Among the 11 evaluated sites, Wadi El Riyada in the Hamata sector was identified as the most suitable rehabilitation location. Following site selection, rehabilitation activities began with seed collection from resilient parent trees located in priority areas. Soil preparation involved mixing wadi soil, coastal sediment, and organic manure to create a homogenized substrate suitable for seedling growth. A particularly innovative component of community engagement was the establishment of community-based nurseries within local households in Abu Ghussun. 2 nursery facilities were developed inside selected homes, strengthening local participation and building practical capacity. Seeds were cultivated under controlled nursery conditions, using specialized soil mixtures and irrigation methods designed to simulate natural environmental conditions. After a 3-month nursery phase, seedlings underwent a hardening off stage, lasting between 2 and 4 weeks, under mature mangrove trees during December 2025. This phase promoted physiological adaptation processes, including activation of salt glands, increased tissue lignification, and development of erenchyma, thereby enhancing tolerance to field conditions. With full participation from park researchers, observers, and local community members, approximately 1,000 mangrove seedlings were successfully outplanted in December 2025, using site-specific planting techniques designed to minimize stress from tidal flooding, wave exposure, and grazing pressure. This rehabilitation strategy emphasized ecological compatibility, community participation, and long-term sustainability. Monitoring and evaluation activities were conducted using standardized scientific protocols to assess seedling performance and ecosystem recovery. Seedling growth was monitored regularly using indicators such as plant height, leaf number, and survival rates. Results demonstrated strong establishment success, supported by adaptive monitoring frameworks aligned with international ecological restoration standards. Based on project findings, several strategic recommendations were developed to guide future mangrove conservation and rehabilitation efforts. These include establishing a formal rehabilitation committee to oversee implementation, expanding rehabilitation activities into additional priority sites, strengthening nursery systems and community participation, maintaining long-term monitoring programs through 2028, and integrating climate change projections into conservation planning processes. This small pilot project demonstrates how science-based planning, early-stage capacity building, strong community participation, and adaptive management can successfully restore fragile coastal ecosystems. Through the integration of technical knowledge and community stewardship, particularly the innovative experience of cultivating mangrove seedlings within local households, the initiative strengthened ecological resilience while reinforcing long-term sustainability. Together, these efforts contribute to safeguarding biodiversity, enhancing climate resilience, and securing sustainable livelihoods for coastal communities.